Hey, welcome to Ones and Zeros. My name's Ben, and today we are doing another episode in our STM32 Basic series. In this particular episode, we're going to be taking a look at being able to write data to the flash memory on the STM32 devices, which can be really useful if you have some particular settings or something like that that you need to be able to save to be able to reload them if the device resets, things like that. Or even being able to do things like storing log data or other bits and pieces in Flash, so that even if the power cuts out to the device, it's still going to retain that data there for you. So a fairly simple one. We're going to go through and actually get a driver written. First up though, we'll take a bit of a look at kind of some of the differences in layout between a couple of the different STM32 devices. But much like we typically do in this series, the particular device that we're going to be taking a look at today is our STM32 F411 Nucleo 64 board. So we'll get a bit of a driver written to be able to write data to the flash there, have a look at how to be able to access it. And we're also going to have a bit of a look at a handy tool for being able to check and make sure that the data is actually being written correctly to the flash as well. So that's kind of the plan for this video. I'd also just like to say a huge thank you. We now have 3 Patreon members, all level 3 members, the highest tier. So thank you to those of you that are helping to support the channel, whether it's through Patreon or even just watching the videos, and those people that are hitting like and subscribing. We've got nearly 300 subscribers now, which is awesome. But let's get into actually taking a look at our flash memory. So we'll jump over to this one, and let's first up just have a bit of a look at the way that the flash memory is typically organized in a couple of different devices. We won't go through a whole range of them, just 3 different ones, because there is some differences, and depending on how you go to access it, those differences are kind of definitely need to be known in order to make sure that you're going to be accessing the right bits of memory at the right time and not doing things like overwriting the actual software that you're putting on the STM32 and things like that. So we're having a look at the reference manuals for the 3 different devices we're looking at today. This is for the F411, and just looking in chapter 3, which is the embedded flash memory interface. If we scroll down a little bit, we'll find this section here that shows the flash module organization. And what we're actually interested in here is the main memory. And we can see this is broken up into 7 separate sectors. And some of them are 16 kilobytes. We've got one 64 kilobyte sector and then a few 128 kilobyte sectors. Now, typically when you go through and you write code and you upload it to the chip, that code's going to be starting at sector 0. And depending on how large that code is, it may take up more than one sector. In the case of the code we're looking at today, it will probably be using the first 2 sectors. And it pays to be aware of that so that we know which other sectors we can erase and write data to without affecting our code. Because if you overwrite the code, you're of course going to cause some rather interesting issues for yourself. So we'll have a look at how to sort of tell which sectors are actually getting written to when we program them as well. So that will be a little bit useful to know. So as we can see here, this particular device has 7 sectors. If we have a look at the F769, which we have been using on the Discovery board in the Discovering STM32 series, we can see it starts to get a little bit more complicated, mainly in this situation because we have the option with this device to be able to have it operating in single bank or dual bank mode. In single bank mode, we've got 11 sectors, and we can see they vary in size from 32 kilobytes up to 256. But other than that, that's kind of similar, unless we actually operate it in dual bank mode, in which case we've got bank 1, which has 11 sectors, and then we've got bank 2, which goes from sector 12 through to sector 23. So it does make it a little bit more complicated, and it just pays to be aware of how many banks you're working with, how many sectors you've got available, that sort of thing. As well as when we go to create the driver, we'll need to know what addresses the various sectors start at and things like that. And we'll also need to know that when we're using our tool to be able to read data from the flash memory onto the computer so that we can actually check and see what's in there. If we jump to our H7 device, which we've got on our Nucleo 144 board that we've had a look at a couple of times previously. This also operates in dual banks. In this case, we can see that we have 7 sectors in each bank, and that all of the sectors for this device are 128 kilobytes. So again, pays to be aware of whether we've got 1 or 2 banks and how many sectors we've got in each bank. And we'll see that a little bit when we actually go through and start writing the driver for that as well. But as I mentioned, you'll find this information in the reference manual for the specific device that you're working with. So we're going to be following on with the code from our Quartz Arc code from the F411, which is up on GitHub. So I will put a link in the description for the code that we do in this episode. So if you want to check it out, you'll be able to jump onto GitHub and grab hold of a copy of it or have a look at it. And that code is free for non-commercial use as well. So if you do want to use it commercially, you need to send me an email and we can have a chat about that. But let's first up get a couple of files created for this. So we'll get the file sorted so that we can create the driver. And we're just going to jump straight into actually creating a driver for it this time around, because it's a fairly simple one, rather than sort of having a look at how it works prior to doing the driver like we've done sometimes. So we've got our files there. Let's just grab a header from one of our other driver files, pop that in there. This will be a flash driver, and its name is Q8E Flash. And what is it today? The 3rd of February. Going incredibly quickly. It feels like only a couple of weeks ago that I started the YouTube channel, but it's been, I think, 4 months or something now, and enjoying every minute of it. So we'll just do our, might help if I spell that properly. Cool, that's that one. And we're going to create a couple of bits that the driver's going to need. So we're going to create a define just to let us know how many sectors we actually have on this device. In this case, it's 8. And we're also going to create a structure that will contain information specific to each sector as well. Just call that Q8E Flash sector data. And that way it just allows us to store an array of structures for the various bits of data for the sectors. So we're going to want to know how large the sector is, because as we saw, some of them are smaller, some of them are larger. 3 different sizes that we've got there. Also going to want to store the base address for the sector. And I'll store a pointer to that base address so that effectively there's a few HAL methods we use when we go to actually erase or write to sectors on the flash. But as far as reading from it, we're basically just reading from the particular addresses in the address space. So if we jump back over to our PDF here, we can see that we've got the particular addresses for the sectors, and we can actually just read data from those as if we were reading data from anything else that's in the address space of the device. So that part's fairly easy. It's more making sure we do the erasing and the writing correctly. So we're also going to have this locked item in the structure as well, so that we can actually tell it to lock particular sectors so that it won't let us erase or write to those. And that comes in handy, so we know in this case, say if we're using sectors 0 and 1 to store our program code, we can lock those so that it's going to prevent us from being able to actually overwrite the code, which would then cause some behavior we definitely don't want to have happen. Alright, so let's get our actual driver done in here, and we're going to do this as a Singleton class, as we've done a bunch before, because we only want 1 copy of this driver. So let's create that guy. And not much we're going to need to store in terms of data for this one. We'll need our data for our specific sectors. Using our define to make sure that it's pulling the number of sectors from there. Keeps everything a little safer and more consistent. I'm going to make a private constructor for this one due to it being a Singleton class. And we'll pop the code into that one in our source file. Now, because it's a Singleton class, we're going to want to delete our copy constructor and our assignment operator so that we can't make copies of the class. Like so. And then in order to be able to access the class, we're going to want a get method. And as you may have heard me talk about previously, with the Singleton class, the constructor being private is not something that we can call from outside of the class. But as soon as this get method gets called for the first time, it will go through and actually call the constructor, and the class will get created at that point. I will have a video coming out in our Unearthing C++ series looking at both normal classes and Singleton classes in the near future as well. So that's that one. So basically all this does is returns the reference to the static instance of the class, so that way we can access the only copy that can exist of the class. And we're going to want some methods to be able to access various things about the sectors, erase them, write to them, all of that sort of stuff. We're not going to need initialization and deinitialization methods with this one, basically because the flash gets initialized when the device is going through its boot phase. So that does help make it a little bit simpler. So we're going to want a method to allow us to get the sector size. And basically give it an index of which sector we want to access. I'm going to check that the sector that we are pointing it to is within the bounds of the 8 sectors that we have, so 0 to 7. We could also use an enum to select our sectors, just have an enum with 8 items. That would work as well. But we'll go with this particular approach for the moment. We can always change it later if we'd like to. And in this case, we're just going to access the size member of the structure for that particular sector. Now, next up, we want to be able to retrieve the base address for a particular sector. So similar to our get sector size method, and just check to make sure that the index of the sector we're passing it is within the bounds of what we want. And if we were to use an enum, we would have the benefit of not having to check whether it's inbound, due to the fact that the enum would prevent us from being able to supply a sector index that's outside of what we're actually looking for. So it could be beneficial to do it that way. Next one is to retrieve a pointer to the start of the sector so that we can read data from it. Bear in mind that trying to write directly to the sector without doing things properly, you probably will end up causing a memory fault or a bus fault of some sort. So that is that one. That will be that one there. And we might also pop on in just to be able to check if a sector is locked. And we'll return true if that's out of bounds. Otherwise, we'll retrieve that from our sector list. Like so. So that allows us to retrieve those bits of information. And then the 3 other methods that we're going to have in this class relate to being able to erase a sector, to write to a sector, as well as being able to do an erase and write in one go in a single method, so that we have options as to how we want to, or how we can go through and access that as well. Again, just passing it an index to the particular sector that we want to erase. And in this case, because we're going to put the code from these in our source file, we'll need to be pointing this to some non-static implementation methods due to using a Singleton class. And these three methods will all return a QA result so that we can check and make sure that things have either whether they've succeeded or failed. In this case, we'll provide it with a pointer to the data that we want to write and the size of the data that we want to write. This particular method will start writing from the very beginning of the sector, whereas the normal write method, which will also will allow us to actually provide an offset in bytes from the start of the sector so that we can do multiple writes to it. It is important though to make sure that any area that you're writing to has already been erased, simply because that's just the way the flash memory works. It needs to be erased prior to trying to write to it. So if you erase a sector and you write a bit of data to the start of the sector and then you want to add some data to it that's separate to that, as long as you're writing in a part of the sector that was previously erased but that you haven't written to yet, then it will still be fine. So you can do multiple writes to the same sector as long as you're not writing to the same part of the sector each time, otherwise you're going to end up with data that is corrupt. So that'll be our offset from the start of the sector in bytes, as well as a pointer to the data that we want to write and the size of the data that we want to write. And we'll create our private implementation methods, which we'll then do the code for in our source file. So our erase methods. Our erase and writes. And our write method. So save that and let's get our source file sorted out. Get rid of this guy. We want to include our header file for that one. And there'll be 4 methods that we need to pop into our source file, which will be our constructor, and then these 3 methods here. Get all of this fleshed out a little bit. always like to make sure that things stay consistent with the code we've written previously as far as layout and commenting and all of that sort of stuff. So just quickly go through and get that sorted. And ready for some code. Alright, so in our constructor, we do need to go through and actually set up the various bits in our array of structures for the various sectors. So first up, we're going to need our base addresses, which here's one I prepared earlier. So again, these are just copied from the reference manual, the start address for each of the sectors. We're going to need the sizes, which again, these are just copied from the reference manual, converted from kilobytes into bytes. So taking the kilobytes and multiplying them by 1048 in 1024 in order to convert kilobytes to bytes. We're going to want the pointers, and for these ones we're basically just making use of the base addresses we've already created and just creating pointers to those particular base addresses. And in this case just using void pointers, so that way if we retrieve the void pointer we can typecast it to a uint8t pointer or a 16 or 32-bit pointer or whatever we would like there. We could also have a structure set up with the particular details that we wanted to store there, and typecast our pointer to that structure so that we could then access it that way as well. Now with this one we'll set it up so that the first 4 sectors are locked, so that we've got all of those sort of set aside for code, which gives us, jump back to here, gives us 64 kilobytes worth of code space that we can use, and the remaining area of memory is set aside so that we can actually write to it or whatever. Again, as long as we're locking the areas that we're definitely using for code, it's going to prevent having any issues where we're going to be overwriting stuff that we don't want to overwrite. So that's that one. Let's get our erase method done. Again, we're just going to copy and paste this code and then we'll have a look at it. So first things first, we're going to check that the sector index that we're passing into the function is not out of bounds, and we'll fail it if it is. We'll check if the sector's locked, and if it is, then we'll fail it. And if it's all of that stuff's good, then we're going to go through and actually do the erase. So the first thing we need to do is unlock the flash using this HAL method so that we can actually manipulate it, because the flash is generally locked in order so that we can't just go through and erase it or write to it or do things that we may not want to do there. I'm going to clear some error flags for the flash just so that the actual erase goes nice and smoothly for us. Then we're going to go through and actually erase the sector, just giving it the index for the particular sector that we want to erase. And then the flash voltage range is dependent on the voltage the chip's actually running at. So in this case, with the fact that it's running on 3.3 volts, we want to use range 3, and we can see if we right click on that and go to open declaration, we can see the various options there. So if we were operating between 1.8 to 2.1 volts, we'd go range 1. But in this case, we're at 3.3. So we're going to go with range 3, as we don't have external VPP on this device at the moment. And then once we're finished doing what we're doing with it, then we go through and we lock the flash again so that it stays safe. Now we'll do our write method next because we're not doing the erase and write at the same time here. We can just look at the write itself. So similar to our erase method, first checking our sector count is within the bounds of what we want, that the sector isn't locked. We'll also check that when we write this data that we're not going to exceed the end of the sector. So if we are providing an offset, then we're taking that into consideration as well as how much data we want to write. And if that's going past the size of the sector itself, then we're not going to try and write the data. And similar to when we did the erase, we'll go through and unlock the flash first, then clear our error flags, calculate the base address that we're going to be writing to. So that'll be the base address of the sector plus how many bytes offset we are from the start of the sector. And then we're going to go through and write the bytes individually to the flash. There is options to be able to write it as half words or 16-bit words or 32-bit or double words as 64-bit. In this case, just to keep things simple, we're just going to do it as bytes, and that way if we tell it to write, say, 3 bytes or 7 bytes or something like that, it's not going to have to try and figure things out based on trying to write 16, 32 or 64-bit values. That way the minimum size that we can write is a single byte. Gives us a little bit more flexibility there. And basically just using the HAL flash program method, telling it that we want to write it as bytes. As I mentioned, there's different options that we can provide there. We'll provide it the address that we're writing to. So in this case, it'll be our calculated base address plus the particular byte index that we're writing to, and then the particular byte that we want put in there. And then just locking the flash again, as we've done for the erase method. And our erase and write sector is fairly similar, except this one only allows us to write from the start of the sector rather than being able to provide an offset. So similar thing, check that the sector index is within bounds, whether or not the sector's locked. Erase it similar to what we did in the erase method. Write it basically the same as we did for the write method, and then lock it again. So it's very, very simple driver. And that's basically all of the code that we're going to need for that one. So let's go through and actually have a look and see how we can use that. Now, we might just compile the code. Actually, we'll do... Which way do we want to do this? We'll compile the code and dump it on the device as it is, so we're not currently manipulating the flash, so that we're kind of starting from fresh. See if we get any bugs. Doesn't look like it. Wonderful. Let's pop that over onto our device. And of course, because I updated Cube IDE the other day, we need to go through and update the ST link on this board. Which thankfully is generally a fairly quick process. That's that done. And let's get the code over there. Nearly done. And it is running and it is happy. All right, so what we're going to do as far as writing the code for the rest of the video, we're not actually going to be doing it from Cube IDE. And one of the reasons for that is because we have the STM32 Cube programmer, which is also a really cool bit of software. So we can use it to be able to program the device, and we can use it to program it via ST-Link, via UART or USB. Has a bunch of different options for being able to do that, as well as being able to do things like view CPU registers and run and halt the software, being able to see the registers for various different devices that we have on the STM32. So similar to what we can do with the debugger in Cube IDE, we can do all of that through here as well. And in some ways it can be a little bit easier to be able to view some of this stuff in the Cube programmer as well. But the reason we're using it for this video is because we have the ability to be able to read the flash from the device. So in this case, we can see we're reading from address hex 08000000, which is the start of sector 0 of the flash, as we saw from the addresses in the reference guide. And we can actually see the code that is residing there. So the cool part about this is when we go to actually write something to the flash, we can come in here and actually read that flash onto the computer so that we can see if the data that we want there is actually being written correctly. So let's go through and actually write some data. So we're going to we might just write a string of characters to it and read them back in the code and make sure that that is working correctly. We're going to use sector 7 for that. So the last sector, one of the 128 kilobyte ones, and we'll just write 9 bytes in total to it. We'll create a string containing the data that we want there. And we'll put these in as individual characters. Which allows us to put the null termination character in there so that when we read it back, we can read it back just as a normal C string and it's automatically going to be null terminated. So let's write that to the flash. So we'll send out a message via serial just to let us know that it's starting that process. We use our erase and write method so that we can do the erase and the write all in one go. Tell it which sector we want to write to and point it and give it a pointer to the string that we want to write and the size of the data we want to write. If it fails, then it'll return a non-zero value, in which case we can print out an error message. And also get serial to put an extra blank line in there before we do the next bit, just so that it makes things look a bit neater in the serial terminal as well, which we will open now. Get that one connected. Now, because we're dealing with a Singleton class, and this is the first time we're actually accessing the class, this is actually when the constructor will get called. So it'll get called prior to it actually doing the erase and write. So when we call this, it's going to go into this static method. And the first thing it's going to do is call get. And when get gets called, because it's being called for the first time and we're retrieving an instance of the class, then it will run the constructor at that point and fill out all of the data for the 8 sectors that we have there. That's kind of how that works. So we'll build that, make sure that, no, we have, might help if we include our new driver, otherwise that's probably not going to work. Try that again. Still have an error. What's going on? Pretty sure it is. Ah, erase and write sector. Okay. That's better. All right. Now, as I mentioned, we're going to use the actual programmer to pop the code on this time around. Oh, we've already got a copy of it running. So we'll close that one and go to the one that's already open. This is already connected to our device. We can see the details for the device coming up here, which all look correct, so we know that that's fine. And we are programming via ST-Link. I'm just going to jump into our programming page. I'm going to grab the binary file for this one, which is going to be in here. It'll be this one, this one, this one, and that's in debug. Grab our binary file and let's program that. Okay, let's try that one more time. Still full chip erase on that. Let's just see. Okay, so it didn't seem to actually be writing to it correctly. Okay. Let's just disconnect that. Unplug our board and plug it back in. Connect to it again. Okay, it was just being weird. All right. Sometimes turning it off and on again just fixes the issue for us. So that is all good there. Let's reconnect that in serial. And we can see it's booted and it's written to flash. So now what we should be able to do is jump into here. And we need to know what sector we are accessing. So that'll be this address here. because it was sector 7 that we're actually writing to. Let's pop that in there, hit read, and we can see that the data that we wrote in there is actually there, which is good. So that tells us that our write is actually working correctly. So now we know that that part is all working correctly. Let's get the code in there to read that back and pop it out the serial terminal. Now we're going to do a few things in here just to double check that the data is actually correct. Which, if you're storing data in the flash, it's worth having like a particular ID or something that you're going to be storing in the flash that's not going to be changing, so that when you read back from the flash, you can actually check to see whether that ID is correct. The reason you want to do that is because if it's not, then you know that the rest of the data that you're trying to read back is probably not going to be accurate, and you're probably not going to be wanting to make use of it. So say if you program to a new board and you're expecting your code's expecting there to be certain settings that are sitting in flash that your program's going to need to be able to run in a particular way. If you have a bit of an ID thing in there and the ID doesn't match, then you can then assume that the settings there aren't written there. So in that case, you can then go and say write a default set of settings there and go with those moving forward, and then write the new settings to it as they change or whatever through your code. In the case of this, because we're actually writing a string to the flash, if the flash was completely erased, which we might actually just do just to demonstrate this, with the string, it needs to be null terminated, which means that the last byte of the string needs to be a 0, which means that if the flash was erased, then when we go to read the string, we're going to run into all sorts of interesting issues. And I'll show you why. I'm going to erase sector, and that will be in that one. Pop out a message saying that we're erasing that, or that we have an error. Cool. Let's just build that, make sure we've got no errors there. Do have a warning from unused variables, but that's fine. And let's jump to our programmer and tell it to start programming. This board's being weird at the moment. Let's just reconnect that. Or the programmer's being weird is what it looks like, so just disconnecting and reconnecting seems to fix that. So we've just run that code that we've put on there, and then if we go through and we actually read from that same area of memory that we wrote to before, because the sector's erased, it's going to be all ones in binary or F's in hexadecimal. So if we were to try and read a null terminated string from here, we're going to have invalid data, and because when you erase flash it sets all of the bits to ones, there's not going to be a null termination there, which means it's going to continue to try and find the null terminator for that string, which doesn't exist. So you would effectively look at locking up the device. Now, say if you had a project where you've got a particular set of settings and you're expecting those different items in the settings to hold data in specific ranges or whatever, if you're trying to rely on those settings being correct without checking whether or not they're correct first, then you could potentially end up in situations where your program's going to do something that's not defined. So if we write a little ID value, say to the first 4 bytes of the sector that we're writing to. And then when you go to first read those settings off the flash memory, you can check to see if that ID value is correct. If it's not, then you can assume that the settings are invalid and that you need to write some default settings or a new set of settings to the flash rather than going off what's stored in the flash. So that's always pretty important. In the case of what we're doing here, rather than writing an ID value, I know what we've written into the flash. That's not going to change. I know that we need to have the null termination character stored in there. And that will be at the 9th byte. So we can double check for that in order to check whether or not what we're expecting is actually there. So we're going to retrieve a pointer to the start of sector 7 just by using our get sector pointer, give it the index of the sector we want, which in this case will be number 7. Create a string that we can write the data into. There's a few different ways we could do this as well, but this will work just fine for us. So we're just going to iterate through the bytes there and copy those over to the string that we've created, like so. And then we're going to go through and actually compare. Actually, before we do a comparison of the two, let's check for the null terminator so that we can have a look at how to go about that. So, going to check the character at string size -1, which will be, or what should be, our null terminator. And if it's 0, then it's not going to go into this if statement because it'll be a false. If it's anything other than 0 or a null character, then we know that it's not correct. So we can just print out a message letting us know that that's not right. And just for the sake of it, we'll also fix the null terminator on that one if it's incorrect. We'll also go through and do a comparison between the string we wrote and the string we're reading in order to determine whether all of that matches or not. Although if the null terminator was wrong, it's a fair guess that the rest would be incorrect anyway. So use string size, and then if that doesn't match that, then we'll make BLComp false, so that if BLComp is false, we know that there has been an error with the data. Like so. And then we'll also print out a copy of what it has actually read back. And because we're replacing the null terminator in a situation where it's read incorrect data, we can still print out the string without running into errors that we would run into if there was no null terminator on the string. So let's check that. And we'll just confirm at the moment we have no string sitting in there. So what we might do is actually not do the write at the moment. We'll just do the read, and let's see what happens if we're reading incorrect data. So I'll just build that again. I'll just disconnect and reconnect the device just so that it doesn't misbehave like it did before. And program that on there. That all worked correctly. We can see if we read it, we've still got that sector completely erased. And if we jump to our serial terminal, we can see that it's read back those values. It's told us that the null terminator was missing and that what it read doesn't match what should be there, what we were expecting. So let's tell it to actually do the write and then the read. Again, we'll just disconnect and reconnect that. We jump into here and read it, we can see it has successfully written the data to the flash, which means if we jump to our serial terminal, we can see that it has actually read that string back correctly. And then finally, let's do one more run where we're not actually doing the write, where we're just doing the read. Because that data should continue to exist in the flash so that we don't need to rewrite it. We can just read it back and it should still be correct. That is slightly strange. Have I selected an incorrect option? Okay, you can actually see in here which sectors it's actually erasing and writing to. So it shouldn't have been touching sector 7. Although if we take a look, our data's missing, which it shouldn't be. If we do our write again, let's jump back to our programmer. Definitely not there. Okay, that's all programmed correctly. Our data's there. Now, if we reset the device and we read it again, data's still there. Let's disconnect it and reconnect it. That's a little strange. What are we getting from here? Let's just restart that. Looks like the program, oh, it is actually doing a write and a read, which means the data's there now. I always like weird stuff going on. Let's just disable the write again this time. Jump back to our programmer. If we check this, yep, we've got data there at the moment. Let's get this programmed. And again, it doesn't want to do it correctly. Okay, we'll disconnect and reconnect. Program it again. I bet the data's... Data's still there this time. So it's actually working correctly now. Okay. Interesting behavior. And the code that we've put on it is not doing the write, which means that the data is actually sitting there correctly now, which is a good example of why you would actually go through and check like have an ID value or something to actually compare, or in this case be checking, say, the null terminator for the string or whether the string's correct. You could actually consider the string as it is in this case as the actual ID. That would work fine as well, because that's letting us know whether or not the data is actually correct or not. Now, curious, if we disconnect and reconnect again, the data's still there. So I'm not sure what was causing that weird behavior before. If you've come across that previously, I do know that when I was doing the testing for this video, there was a couple of bits of weirdness. In a very similar manner where it was misbehaving a little bit and then it just started working flawlessly. And I noticed that I was having more issues in some ways from the programmer in CubeIDE than I was with this one. But if you've come across stuff like that before, definitely leave a comment. I do find that interesting. But we can see, let's disconnect it. We'll unplug the board so it's completely powered off. Plug it back in and reconnect it, and let's see what we get. Our data's still there, as it should be. And if we reconnect serial, clear that and reset the board, it's reading it correctly, and we can see it's not actually doing the write, it's just doing the read back from Flash, which is the behavior we should be expecting from the Flash. So that's how we make use of being able to write to the Flash and read data from the Flash. Aside from that little quirk that we saw there, which I will have a little bit of a further look into. That's kind of how that works. Again, make sure that you're referencing your documentation for your specific STM32 device as far as how many banks you've got, how many sectors you have, what the start addresses and the sizes are for the particular sectors for your device as well, because that's all important. As well as, if we jump back to here again, open up our programmer, having a look through here, and you'll see similar information if you're programming from CubeIDE as well. If you scroll through the list of info, we can see which sectors it's actually erasing when it goes to program the device with our code, wherever it is hiding. There we go. So erasing internal memory sectors 0 and 1, so that we know in this case it's using sector 0 and sector 1 to store our code. So that helps you to figure out which sectors you don't want to be writing data to, because then you'll be overwriting code. And that's why, as we showed with the driver, you can set it so that particular sectors are locked, so that the driver will not actually allow you to overwrite sectors that contain the code. So that helps make it kind of useful. It is really useful to be able to store various settings and things like that, or log data, or various other bits and pieces. So I hope you found that helpful. A big thank you to all of the people that have been watching the videos. It's really awesome. I think we're not far off 5,000 views in total since the channel started, which is really, really cool. Thank you to all of the people that like and subscribe. If you did like this one, would love it if you put a like on the video. And a huge thank you to our 3 wonderful patrons that are helping to support the channel as well. If you do have any questions about this or feedback or anything like that, feel free to leave a comment under the video, or you can also jump onto our subreddit or send me an email if you prefer to do that as well. And I will also pop a link in the description to our GitHub repository, which will have the code in from today as well. So hope you're having a wonderful day or night or morning or evening, whatever it is in your part of the world as you're watching this. And thanks for watching.